Interesting, a new topic today, functions, something that you might not have seen before. Although some of you might have seen it in high school or a previous class, but this is a very important topic in math, very useful. It's not that complex, just some concepts. We're going to learn a bunch of new words and concepts today. Please pay attention to all those words and remember what they mean. Once you know what they mean, it becomes very easy to do the homework and do the questions quickly based on the understanding. All right, you guys see my screen, right?
Yes.
Yes.
All right. So first we're going to start by, learning the difference between relations and functions. And after that, we're going to look into some actual functions and notations or formulas. So let's first understand the difference between the two. So relations. I'm going to start with a letter table here. 2 columns. Let's say we have maybe students. And probably some ID. Okay, just some random numbers here. Okay, so this table here is 2 columns, as you can see, and 3 rows or 3 records. Okay, each one from here, each value from here is related to a value from this column. So this forms a relation. Okay, a relation is just a name, another name for table, because there's a relationship between the 2 columns. For example, student A is related to this ID 1, so we can write this together. A has the ID 1, student B has the ID 03. Finally, C is related to
04.
04. So that's basically what a relation is. It does information that's related. And we call these, when we write it in this way, we call this a pair. So a pair of values, this one and this, and so on. We call them ordered pairs because they're not random, they're related, and they're based on this some information. So we call this ordered. Ordered pairs. And basically any table is a relation, but some of the relations are strict and some of them are not. What I mean by that is, for example, here, one student can only have one ID. One student from here can only have one ID, and so on. Certain cases, you may see an element from here with 2 values from here. For example, you may see XYZ, and let's say 7, 2, maybe 5 here. You may see an element from here having 2 values, which basically makes this not a function. Okay, a function has to be 1 to 1. 1 from here has exactly 1 from here. But whenever you see one element from here having 2 elements or more from the other side, that's when you say not a function. Because X has 2 values, has 2 corresponding.
So the things that are in parentheses, a comma 01, is that a function or a relation, or is both?
We're getting our second values from the left side. Okay, so this one here, we said each element from here has exactly 1 value. So this makes it a function. So this is the function. And this is here just another way of writing this, this table. This table is a function. This is also a function. So as opposed to this one where x has two values from here. So always think of it this way. If you see one element from the left having two elements from the right, one element from the left, if it has more than two elements from the right, then that's not a function. It's just a relation. However, this is fine. Two elements from this, x, y, and z, they may share the same value. For example, two students may have the same age, for example. Here, one student cannot have the same, or two of the same thing, for example, two IDs or two dates of birth. So this part, exactly this part here, makes this not a function. Okay, let's do, let me show you another example. Let's say 3 students, and they both have, let's say, the same.
Can you move your page up, please?
If you have, for example, 3 students and they all have, let's say, x is the age. Is that possible?
Yes.
Yes, so this is fine. So we say it's a function. So this is a function. But if you see something like this, let's say one student here, let's say student, and this is, for example, the age of the student. Is this a possible scenario? One student having
No.
3 ages? No. So this makes it not a function. So this doesn't make sense. Not a function. That's pretty much the difference between relations and functions. By the way, both of these are relations. Both of these are relations, but some of them are strict, 1 to 1. One from here has exactly 1 from here. One value from here also has exactly 1 from here, and so on. But you cannot have 1 from the left having more than 1 from the right. It would make it not a function. Okay,
So
so
all
that's
of them are relations, but not all of them are functions.
exactly. Everything is a relation. Some of them are strict. Some of them are 1 to 1 and are called function. Okay, so that's the difference between functions and relations. Let's look at another example. Let's say you have let's say we have something like this. I don't need this one. Okay, so what do you think of this? Is it
Function. It's a function.
It's a function.
Exactly, it is a function because you look, each element from here, x has exactly 1 value, y has exactly 1 value, z has exactly 1 value. That's it. So this is a function. Now, if you look at an example like this, let's say a is related to 7, b is related to, let's say, 7 and 5, c is related to 4. Is this a function?
Not the whole thing.
No,
Why
Is
not?
it always related from
because
right?
the B.
Because of the b.
Is
What
it
about
always
the b?
related from left to right?
The B is related
That's
to
right. The b has 2 values, right? So the b, one student, for example, cannot have 2 IDs. Think of it this way. And when you see a scenario like this, 2 students can share the same, for example, age. Okay, so that's the main difference.
Is it always compared from left to right?
That's right. So we start from here and we link it to the right side. So let's write this, what we did here, let's write it in a sentence. So let's phrase this in an easy, proper way. So function, in a function, for example, each element from the left side, the column, maps to exactly how many values from the right?
1.
Exactly. One value. Okay, so exactly one from the right. That's basically how we tell whether something is a function or not, and always think of it this way. It could be like this. It could be written as a table, or in this form also. I'll show you now how to tell if you don't have a table. If we have just this notation, if we have this, how can we tell whether this is a function or not just by looking at these pairs?
Because B would have 2 values versus 1 for each.
That's right. That's right. Let's see that in this example. So that's what we call set notation. Set notation is basically this. We're going to add a name to it and some braces around it, and we call that the set notation. So just another way of writing tables. So let's take these very examples here. So let's take the first one here. So we're going to give it a name. So let's call this one, for example, R1 or relation 1, right? Then after the name, we need colon, 2 points here. Right after the colon, we open curly braces.
Wait.
Not parentheses.
The
not
one is more than the R?
The
Or that's
R, just the name of whatever relation you have. For example, this one, I'm going to call this R1. We're going to call this R2 for relation or function, whatever it is. Any name, basically, whatever the elements might be. Okay, so you need a name, colon, curly braces. And then inside of the curly braces, we're going to write all the ordered pairs. What are the ordered pairs of this relation?
Did you say that the set notation is always in between parentheses or brackets?
Brackets, this
curly braces.
Curly brace, not parentheses, not brackets. Okay, now we're going to write all the pairs. Just tell me all the ordered pairs from this.
X,
XO
Okay,
Zero,
X03.
Y03.
Y03.
Okay, so you need a comma, and then I'm going to write the second one, Y03. So we get this
Z0.
one.
Z03.
That's right, Z06.
06.
Don't forget to close your curly braces. So this and this are pretty much the same thing. They're just written into different forms. We have the exact same information. So we said this is a function, which is good, which is fine. Let's write the other one here.
Teacher, before you keep going, what's the R1 mean? And then can you also say then what's in between brackets or parentheses? I got super lost there.
Yeah, like I said a couple of times, this is R1, meaning relation. Okay, R for relation. Okay, and also we're going to call this one R2 for relationship.
And then the only thing that goes in parentheses that would be considered a function?
Right. Just let me finish the explanation first for a couple of minutes, and you guys can ask questions. Because ahead of me, just let me finish. I repeat myself a lot. Don't worry, I'm going to repeat it as many times as needed. So let me finish first. So we're going to call the second one R2. Okay, this is relation R2. That's the name of the set. Then after the name comes the colon, the 2 points. Then you open your curly braces. And inside the curly braces, what goes again?
A07.
That's right. All the order pairs from here will go inside this. And that's all. The name, colon, and curly braces. So the first order pair is A. There is 7. Then you need a comma. Once you finish one order pair, a comma, and then the second one, B07. What is the next one?
05.
B05. And then finally, the last pair from this CO4. We'll just C4, and don't forget to close your curly braces. That's all. So this is again what we call set notation. Any table or any relation like this, or a table, we can transform it into this another form called set relation. Again, you need a name. Could be anything, letter, whatever name you may want to give it. Let's say you have fruits here, or you have animals, or you have people. So you would call this, for example, people, or students, or fruits, whatever. Name, colon, curly braces, and you list all your elements inside. Don't forget to separate them with commas, and they go inside these curly braces. Okay, does that make sense to everybody?
Okay, the only one question I have, the B's, we separated them. I was just wondering if there was any way to write them together, like B, comma 07, comma 05.
That's what I did. That's what I did, and then I erased it.
Okay, so that's a very good question. This is the reason why I wrote this here. So this one we said is a function, right? The first one we said is a function. Each one has exactly one value. Each one has exactly one value. As you can see, they're not repeated here. X, Y, Z, they're unique. What do you notice about the second one? B has a problem, right?
Yeah.
It has two values. If I didn't give you this, would you be able to tell that this is not a function by looking at this?
Yeah, because B has two values.
Exactly. That's the point I was trying to make. So
Also,
B here, as you can see, even if I didn't give you this, even if you don't see this here, you can easily tell from this one, it's a function because these are unique. They're not repeated. However, this one here is not a function because the B is repeated. So this a function. First elements are these things. The first values are distinct or unique. They're not repeated, in other words. But this one here, not a function.
Because the first value is repeated.
Exactly. Because B is repeated. Okay, everybody got this idea here? That's the whole thing here about the set notation. It's very easy to tell whether something is a function or not. And you can turn any table or any relation into something like this. Okay, any questions, everybody? All right, so let's, so again, there are multiple ways of writing down information. As a table, for example, in a relation set notation, or in a relation like this, we can tell in each one whether something is a function or not. We talked about this just by looking at the relations between the elements. Or if you have a set notation, just by looking at the first elements only and see if they're repeated. If one of the elements is repeated, it's not a function. But if all the elements are unique or distinct, then that's a function. Let's look at another form now. So in addition to this, we have another form of presenting information. But before that, let's talk a little bit about another new term or terms, domain and range. Okay, again, if you take an example like this and you have again, is this a function or not?
No.
It's not a function because basically the A. But if I remove this line here, now we have a function. Each element from here has exactly one element from there, which is good. we call these elements, all these elements together, we call them the domain. Okay? And all these elements, we call them the range. So the domain is the left side, the range is the right side. And we can write these separately together in this form also. So we can say the domain in set notation, so set notation. So a set needs a name, as we saw, a name, colon, curly braces, and some elements inside. Same thing here, so the name is domain for these elements. Then, again, colon, and you open the curly braces. And what elements go inside the curly braces?
ABC.
That's right, so the domain is A, B, C, A, comma, B, comma, C. Then the range is same way, so the range is the name, colon, and what are the elements of the range in this case?
0, 1, 0, 3.
That's right, these elements, and usually arrange them from the lowest to the highest. So in this case, they're already arranged. So all that it means, okay? No big deal, nothing else. Domain is the left side, range is the right side, and that's all. And you can write them together here. So basically, instead of writing two groups like this linked together, we can write them separately here. And
But then in that case, how would you know if you have a domain and a range set notation, how would you know which domain goes to which range?
this will not be given to you by itself.
Oh,
Okay? Okay. So you will see this and you will be asked to write this. Okay. If it was about the domain, whether it's a function or not, it will be given to you like this together. So basically here, when you put these together, you get these pairs relation sets. So let's put these two together. Let's call this whatever relation it is. R for relation or any name, colon, and curly braces. So domain, range separately. Let's put them together in order pairs. Okay, what is first order pair? So not looking at this, we need to look at this because here, this doesn't tell us what kind of relationship is between the values, but we need to go to the table or the relation first. So what's the first pair?
8,01.
That's right, A comma 0, 1. Then?
B,03.
That's right, another comma and?
C,05.
C 0, 5 and close. Okay, and just if you ignore this, again, how can you tell whether this is a function or not?
No repeated domain.
Exactly, so A is distinct, B is distinct, C is distinct, so that's a function. So if you have this, if you domain by itself here, range by itself, together they make this. These again are pretty much the same thing. So these are the same thing, we just write them into different forms, but they contain the exact same information.
So
would you,
they, oh, I'm sorry.
No, go ahead.
Okay, so they would give you the A, like the table, and then maybe ask you write the set notation as domain, range, and then also write it out like the R form. Like,
that's right, yeah. So when I give you something like this, I will tell you what is the domain of this function. Write the domain in set notation, or write the range in set notation. Then I may ask you to write this in the whole table in or relation in set notation or relation set. Another name for this is a relation set or set, as we say here, set notation.
So, teacher, would you be able to then describe functions as a set of order pairs in which the left component of each order pair is unique?
That's right. You can say that. That's pretty much it. You just rephrase this, but that's right. You're correct.
Okay, it's because I was confused if by function was one parenthesis or all of the parentheses together.
So a relation is this. So this and this are exactly the same. This, we just separated the elements. We wrote the domain by itself, the range by itself. This does not tell us the types of relations between the elements, but this does. Again, these are the same, as I said. These are equivalent. They have the same information. You can tell whether it's a relation or not by looking at those. Okay, so we need the original thing. This is just the elements together. It does not tell us whether it's a function or
No,
not.
I know that. I was just confused in how to differentiate a relation and a function.
All right.
So all functions are relations, but not all relations are functions. So if it's a function, if there's no repeated domain in the set.
Okay.
So that's right. Yeah, just remember this example here and also here. That's how easy it is to tell whether it's a function or not. Let's move on to other things now. So in addition to tables and these relations and the relation sets, we have another way of basically presenting the same thing. We have, can you guys think of another form of presenting information other than tables or relations?
A graph.
A graph. Very good.
Not the graph stuff, Lord.
Graphs and relations. Probably the easiest and the most convenient way of presenting information is graphs. Nobody wants to go through a table with multiple hundreds of rows and columns. But if you see a graph, you can immediately tell what's going on. For example, if you have a graph like this about the sales or something of a company, this, you know, in 2 seconds, you can tell what's going on. For example, June here, I don't know, this is 10 million sales or something. So you can say, oh, the sales went down in June and then picked up again and went up to maybe around 20 million or 30 million. So graphs, you can see the information in literally in seconds. But if this was a table, it would
I
take
almost
you,
went and draw that.
if this was a table, it would take you minutes, if not hours, just to understand or interpret the data and how it's going up or down. So graphs are very convenient. They're visually appealing and easy to interpret and understand within seconds. So let's look at some of the graphs here. And I'm just going to draw a few here.
Are you gonna erase these?
Right now, I'm going to keep these.
Okay.
Okay. So these are two-dimensional graphs, as you know. This is the x-axis, the y-axis, for all of them. And in these graphs, we can, this is basically the empty graph. We can put functions, we can put relations, different forms, different shapes. Then we put those in green. So we're interested in these here, in the graphs in green. Say this one, maybe another one like this, something else like this, and possibly be a circle like that. Don't worry about this graphs too much now. I'm just giving you the shapes. Just look at the shapes. We're going to learn later how to make these ourselves. All right, so for here, we learn how to tell whether it's a function, well, by looking at this, the first elements. It's also just as easy to tell whether graph is a function or not. So again, all these are relations. All of them are relations, but some of them can be functions. Here's what you do. You just imagine a vertical line going through the graph. So if you imagine that vertical line going through the graph, how many times will that line, this line here, the red one, how many times will it meet? Does it meet the graph?
One.
Just once. Over here it meets once. What about here?
Twice.
That's right, it meets twice. Here and here. And if you look at the, okay, good enough for now. So here's the deal here. So if the graph, if the line meets the graph once, it's a function. Okay? If it meets more than once, not a function. That's all. That's all what we call the vertical line test. Again, if the vertical line test meets the graph once, it's a function. If it meets more than once, for example here, not a function. That's what we call the vertical Let me write it down here for you. So if the vertical
And it's only done vertically.
That's right, only vertical. So if the vertical line meets or intersects with the graph, meets the graph once, it's a function. Okay, it's a function. Otherwise, not a function. If it meets more than once, if the vertical line meets the graph more than once, okay, so it's important, more than once, it's not a function.
Sorry, Professor, what does it say on the first line at the end? If the line meets the graph once, it's a what?
It's a function.
It's a function.
And it could be the line anywhere.
That's right. Could be anywhere you
That's
imagine it. Yeah, you can imagine a line anywhere. If you see it anywhere, if you see it meeting twice, then it's not a function. All right, so let's try this with the next couple of problems. Is this a function or not?
Yes,
Yes.
Yes. Why is that so?
Only
because
once.
it only meets once.
That's right. Anywhere you imagine that graph, you will only meet the graph, the green one, exactly once, which is fine. So that's why, just like here, these are unique. Each one has exactly one value. Same thing here. Each point from this has exactly one x value, as opposed to this one here.
But for example, in the ones that it meets twice, there's one which would be negative and one that's positive.
Not necessarily, as long as it meets. It could be, for example, here, could be like this. It doesn't have to be negative or positive. The next one here, this whatever shape this is it a function or not?
No.
Not a function.
Not a function.
Not a function, that's right. Because this should be a straight vertical line, okay? So let's assume that it's not a curve, just a little. And again, this meets twice. So function, not a function. This one, function. And this one here, not a function. Okay, pretty simple stuff. Just remember all those key terms, and all the answers to the questions can be very simple. Okay, just know what your know the definition or the meaning of the terms, the understanding of the concept, and you can easily answer questions, like I said, within seconds. For example, these graphs may look complex for someone who just walked in right now, sees this, may think it's something complex or difficult, but again, just testing with a vertical line to see whether the graph is for a function or not. Okay, so any questions, everybody, so far? Okay,
No.
so let's look at something else now. Another form of the function now. So we saw table, we saw groups, we saw set notation, we saw graphs, but we didn't see the function itself. The function itself, or the actual formula with the x's and the numbers, we didn't see that yet. So let's see how that works. Let's look at the actual thing, where all this comes from, which is basically a formula or an equation. We're gonna call that the function notation, the actual function itself, that we've been talking about the whole time, but we haven't seen yet. All right, so function notation. This is the notation here. We use f.
Sorry.
F for function, and then X in parentheses, an equal sign, and some value here. That's what we call the function notation. So each function has a name, could be F, could be any other letter, G, H, K, any letter basically. We have a variable here inside the parentheses, and then you have something, some value out, or that's related to the X. Just like we saw earlier with the values, for example, A related to 0, 1. So this is an ordered pair, which is basically, in this case, in general, we say X and Y. So X here and Y here. If we put, for example, for the previous relations or functions, if you put A here, the corresponding value will be 0, 1. So F is the name, X is the variable, and of course, Y is the value. The value of corresponding to this X. So each X has a value of Y corresponding to it. So that's basically how we notate functions, how we write them. And when we plug something into a function, basically, we plug some X, we get some Y back. We're going to see some examples of how that works. For example, here, we'll look at, let's take one of those tables again. Let's say A corresponds to, I don't know, 0, 1, B maybe to 0, 3, and C to 0, 4. What this means is, if you plug A into this formula, you get the corresponding value back. For example, if we plug A, we get 0, 1. The corresponding value to B is 0, 3, and so on. So we can write it this way. We can say F of this value gives us this. F of A in parentheses equals 0, 1. As you can see, this is an ordered pair, A, 0, 1. What is F of B?
FB
0, 3.
03.
That's right, 0, 3. And finally, F of C is
It'll be 0, 4.
0, 4. Okay, so the way we read this, let me write it somewhere over here. So we say F of X is Y. That's how you read this notation here, the function notation. F of something, you get something back. Again, because these are related. It's like asking, what's the ID of student A? F of A is 0, 1. What is the ID of student B? F of B is this. So in math, that's basically how you interpret that sentence and that request or query.
So X is the domain and Y is the range.
That's right. We still have this as a domain. The first elements, as we said earlier, make the domain, and the other ones make the range. And of course, together they make an ordered pair. Now, this is a table that I made up with some random students and IDs. Now, let's actually look at an actual function and see how to generate something like this. See how to get a table ourselves.
I have a question. When this is written, it's always written like X and Y, or do they use like other variables and values?
You could. This is just a generic thing. You could use any letters here. Even for the function, you'll see that sometimes we call it G or K or H. It doesn't really matter. Same thing here. Could be anything. Could be A and B, whatever you want to call it. Doesn't matter.
All right.
So now let's see an actual function and see how to make our table based on a function or a formula. Let's call that. Let's see an example of a function. Let's say f of x is maybe x minus 1. Okay, so again, the name, this is the x of the variable, and this is the actual formula to get the y from. Okay, so this is the expression or the formula that will give us the y. If we plug some x, we plug it here, we do some math, and it gives us some y back. So let's make a little table here. So we have x and y. I'm going to plug some x values here, maybe 1, -2, probably 0. So each value from here, we plug it into the formula here. We simplify this, and we get our value back. This value we talked about, or this outcome here, because it's not random. It's related to the value of x. It's very simple to do, just like simplifying algebraic expressions. When you plug the value of the variable and you simplify, that's pretty much what we're going to do here. So we're going to find all of these. We're going to plug 1 here and here. We're going to say f of 1 is, so we're going to plug the x here, the 1 here, and also here. What would this be?
0.
1 minus 1, which is 0. All you do is plug the x here and here. This x, this will be given to you. The table will be given to you. Or in certain cases, you will be able to make your own table with any values you want. So the missing value here is 0. Okay, so let's find the other one. So f of 1 is 0. Now let's find f of -2. So we're going to plug -2 here. What is f of -2?
-2 minus 1.
-2 minus 1, which is
Negative.
-3.
negative. Very good. Last one, we need to find f of 0. If x is 0, what is the y? So we're going to have to plug that here. So 0 minus 1, which is
-1.
negative 1. That's it. So we completed the table. As you can see, as I told you earlier, if you have a function, that's the original form of the function. You can make a table with it. Let's turn this into set notation. You can turn it into anything you want now that you have that table, because you have the original equation or formula for that. What is the set notation here? Let's give it a name. For example, f, right? What comes after the name of the set?
The colon,
Colon, then?
curly bracket,
That's right, curly braces. And inside, we're going to list all the order pairs. What are the order pairs?
1, 0.
That's right,
1,
the first
0,
one, 1, 0, comma.
-2, -3.
That's right, comma. And
0, -1.
-1. Don't forget to close the parentheses and the curly brace. So from here, we have a table. We have this set notation. What else is missing? What other form of
The graph.
You can do the domain and the range.
that's right. So we can call this, this is a domain and this is a range. Okay, so domain and the range. Or we can write them separately. We can write them in a set notation as well. What else is missing? Other form of presenting information, that's
Graph.
The graph.
a graph, that's right. Function, we have this, domain range, we have set notation. Now let's do a graph. So it's very simple to get the graph of this function. You're basically going to use these pairs, all these pairs. But first we're going to need a bidimensional graph. Should be a straight vertical line or something close to this. Okay, XY, as always. Put some numbers here. As you know, we have positive numbers here, negatives here, positives up, negatives down. 1, 2, 3, -1, -2, -3. And same here, you have +1, 2, and 3, -2, -3, and so on. If you need more values, you can put those. Nothing, it doesn't have to be accurate now. Just
Do we always have to put the numbers, or can they just be assumed?
you can put maybe just the numbers you need. You don't have to put all of them, but at least enough as needed. So now we're going to take all these pairs. What does each one of these pairs represent on a graph?
A dot.
A dot, that's right, a dot or a point.
Coordinate.
So each one of these is basically x and y, as we saw here. Because we plug x, we get y. So now we're going to plug this here. So we start from the x. We're going to start from the x, and then we go to the y. The x is always here. So the first value, always find that over here. So 0, 0 is in the middle. Both x and y are 0, 0 here. This is what we call the origin or the center of the graph. So we're going to start from x. The y is 0, so we're going to stay there. So the x1 is here. The y, instead of going up or down, because it's 0, okay, we're not going up or down, we're staying right here. So we start from here, and we stay there. So that's the first point. Then the next one, we have -2, -3. Again, these are x and y. Where do you start and where do you go?
Start on -2 and go down to the -3.
That's right. First locate the x, which is here, and you go up or down?
Down.
Down 3 units, all the way to -3. So go all the way to here. That's the second point. Then the third one, 0, -1. Okay, so someone tell us where to start, where to go?
Start on this origin,
0 and move over to
and then you go down to -1.
That's right. So 0 is right at the center. Both x and y are 0 here. Then we go down once because it's negative. If it's positive, you go up. If the y is positive, because this is the y-axis, you either go up or down or stay there if it's 0. So 0, -1 is right over here. Okay, so what do you guys notice about these points?
It doesn't repeat. It's a straight line. Well, it's a diagonal line. And then likely a function.
It's a straight line, right?
Mm-hmm.
Let me see if we can grab a line from here. That's good. So our line, or our graph, is a straight line. So for this function here, we started with, the graph is a line. That's why we call this a linear function.
Oh.
Okay. What exactly makes this a linear function? If you look at it, look at the variable. There's something specific that makes this a linear function, and therefore its graph a straight line. Think about linear equations. We talked about linear equations before. What
One
makes
variable?
There again?
One variable?
Not the fact that it's one variable, but if you think about linear equations that we learned before, what makes an equation linear and not some other type? What makes it first degree?
The equal sign? I don't know.
What sign?
The equal sign? I don't know.
Not exactly. We saw linear equations or first degree.
It only has one power.
Okay.
What's that power?
1.
The 1? Yeah, you mean the highest power is 1. That's right. So
Yeah.
just like linear equations, linear functions, the highest power in all the variables is 1. If that's the case, then you expect your graph to be a straight line. Cannot be anything else. Cannot be this or this or this. It has to be a straight line if the power is 1. If the power is 2 or 3 or 4, it will be a different function with a different graph.
So you call this a linear equation?
Linear function.
Linear function. Linear equation is something like this. That's what we saw before. Linear because
it has the function.
But this one has a name, has a function notation, as we saw earlier. So this is a function.
And you would only know that it's a linear function by drawing the graph.
No, you would now, from now on, you can tell just by looking at the power of the variable. If it's 1, it is a linear equation, a linear function. Otherwise, it will be a different function. Let's probably do.
1 second. I think what she's asking is, well, anyway, what I interpreted. She said, how would you know that it's a linear function by looking at it? Isn't it because the f is in front of the parentheses with the x? And then also the power is 1?
Because of the power is 1, and this is again function notation. That's how you know something is a function when it's in this form, the function notation. Okay, so this tells you the shape of the graph. the power, and this tells you that it's a function because
Wait,
of the
what tells you the shape of the graph?
Yeah, the power tells you the shape of the graph.
power. The
Okay,
power
so the
tells
first
you.
one is going to be a straight line in whichever direction.
That's right. The power of the variable gives you an idea of the shape of the graph. So from now on, whenever you see the highest power here is 1, could be 4x to the first minus 11, whatever. If the power of the variable, the highest one is 1, then you know it's a straight line. Let's do another example, maybe with a different power, and let's see what kind of graph we're going to get. Let's
That's
do
a
an
good way to
example.
figure it out, because if you graphed it and then it's graphed in a different way other than a straight line, you know you did something wrong.
That's right. And that's exactly the reason. So from in the future, whenever you have something, graph this, you should know in advance that this is going to be a straight line. If you get 1 point here and 1 point there, you know something is wrong. It's got to be a straight line. So you got to go back, check your signs here. It's very easy to make a mistake in these signs and have one of the points off the line. So they got to be on the same line, not here, for example, here. So you can have a straight line.
Teacher, and the power only goes after the equal sign, right?
That's right. Yeah. Let's look at another example, another function. Let's call it, for example, h for now, and h of x is, let's say, x to the second, maybe minus 3.
Also, the function doesn't need to have the f every time?
Does not. You can call it whatever you want. This is just a name and notation. You can give it any letter, any name you want. So now we have this function here. As you can see, the power is different. So it's not a linear function. It's not a first degree. It has a power to it. So let's see. Okay, I already know the shape of the graph, of course, but let's say we don't know yet. Let's find out how it is. And from that point on, once we know what the graph looks like in the future, you can assume you know in advance how it's going to be looking like before you start graphing it. So name, variable, and this is the expression. We're going to take a few values here. So you need a table with some x's and y's. And again, this table could be given to you. If it's not given, feel free to make your own. Take a few numbers, okay? Small numbers, positives. Take a 0 and also some negatives. That's how you make your own table if you don't have one. Again, a couple of positives, 0, and a couple of negatives. Now we need to complete this table. How do you complete this table again?
By plugging in x.
So complete the table. I'm going to plug all these here one at a time, plug it, and simplify. That's what we call evaluate. So complete a table, so we're going to evaluate. Evaluating the function. All right, so we're going to start with this one. So f or h of 1, not f. We're using h this time. What is h of 1 again? We're going to put 1 here, 1 here. So it'll be 1 to the second minus 3, which is negative 2. All right, then h of 2. I'm going to plug the 2 here. Be 2 to the second minus 3, which is 1. H of 0. We're going to put 0 here, which is negative 3. And h of negative 1. Negative 1 to the second minus 3. Be careful here when you have a negative number. You have second power, so you've got to put that in parentheses. What is negative 1 to the second?
1.
What is it? Negative 1 to the second power?
1.
1. So it's a positive number. We have 1 minus 3, which is negative 2. So negative 2, and finally, h of negative 2 So again, we're going to put the -2 here and simplify, so it'll be -2. The second minus 3. This is 4, right? And 1. Let's put all these values here. Each of 1 is -2. Each of 2 is 1. Each of 0 is -3. Each of -1 is -2. Each of -2 is 1. Good, so we have our function, we have our table. Now let's see how the graph looks like. Okay, let's make a graph. We're gonna need a two-dimensional graph again.
It's a function.
And you need a two-dimensional graph. Again, we have x, the y coordinate. We have some values here, positives, 1, 2, 3. Also some positives here. If you have a graphing paper, you can use it. It's easy, you can just print it out online. Or you can use your ruler and make things accurate.
When we do this, do you want them to be super accurate, or you're okay with just giving you the information?
That should be good enough. Should be good enough to see the shape of the graph. But let's just use your ruler and paper, just to make things clear. All right, so we have this graph that's empty. What do we do now?
Put the XY values to find the point.
That's right. So each one of these is a point. Each one of these is a point on a graph, or a pair, for example, 1 and 2, -2. So x and y, x and y. The first one, x, -2. Where do you start? Where do you go? Start from the x1.
X1.
That's right, which is here. And you go
Down.
down to -2. -2 would be here.
-2.
Then start from 2, go to 1. x2. Again, the first one is always on the x,
Up
on the
to 1.
x-axis. And then go up once, right?
Up 1.
That's right over here. Let me use a different color for the points. All right, now we need to go to 0 to -3. Start from 0
in the middle.
and go down, right? Go down here to -3. This is -3. 3, 4.
-2 and 1.
Okay, so -3, -4. Then 0, -3 is here. What's the next one? -1, -2. So x, -1, which is here. And then you go down to -2. Go down all the way across from here. So -1 all the way down to -2. What else? The last point here, -2 and 1. Where do you start and where do you go?
Out of -2 and then go up 1.
That's right. Start from x, -2, go up once. Go up once. 1 is here, so we're going to go like this. Can you guys see the shape of the graph now?
Yes, it's a U.
A U.
The U-shaped graph. That's right. The U-shaped graph has a specific name.
Parabola.
Parabola. That's right. Who said that?
I did.
Catherine. Good, good. You should be proud of yourself. How did you, when did you learn that?
A long time ago.
Long time ago. Okay, gotcha. All right, so now the trick is to join these together. All these points here, they're going to make a U-shaped graph or a parabola, something like this, not a V-shaped graph. Okay, it's not a V-shape. Don't try to align these. It's not going to be like this. This is wrong. It's going to be a U-shaped graph. It's a little bit hard to do here on the screen, but let me try. I'm going to do piece by piece. So it starts from here, goes down. Oops, just the last part. And there you have it. We call this a parabola. Okay, so parabola is this U-shaped graph. You may end up like this, or sometimes you may end up downwards. So it's not a problem. If you see this in the homework or it's facing down, that's okay. It's just the shape of the function. Depends on the numbers and depends.
Can it shape sideways?
Not for this function now.
Oh, okay.
You
Just
cannot
as
face.
Do we have to know the name?
Say again?
Do we have to know the name?
Well, now that you know it, you, I mean, yeah, you learned it now. If you see it next time somewhere, you know what it is, right? Okay. So, yeah, you might see this somewhere. And now, what's the conclusion here?
that is a function.
Yep, that is a function. So when you have a, yeah, so it is a function because we saw a graph like this before. You can think of what the vertical line does, or you can think of what the values here. Each one has exactly one value. But you can also see it from here. We said earlier, this is a function. So what is the power of this function? I mean, what's
2.
So when it's linear, the power, the line, the graph is linear. When it's power 2, so it's always going to be either this or this. Okay, so from now on, whenever you try to graph a second degree function like this, or a quadratic function, now that the graph will be a parabola. So this is what we call quadratic. Because of the power 2. And the graph, again, will always be up or down a parabola. And each degree, basically, each function,
What's the name
each
of
degree
what?
has a specific graph. Sorry, say it again?
It's a what?
Parabola.
You're talking about this?
Yeah, the name you just said there.
Parabola.
P,
What?
parabola.
Yeah, parabola.
Not the P, the Q. Go up.
Quadratic. This is a quadratic function because of the power 2. And that's pretty much your introduction to functions. I know this was a lot of information, a lot of new concepts and terms. Understanding this is very important and critical for the next couple of classes on functions. So I highly recommend that you rewatch this, especially for people who still have, some confusions or anything. Just rewatch this, and the concepts themselves are not complex. Just remember each term and what it means, and you can easily answer questions, like I said, in seconds once you understand the concept. I'm gonna upload this as usual. Go over it and let me know by next class if you have any questions from it. This is 3.5, 3.6 from the homework. I'll post the homework, but it will be not this week, the next week. All right, I believe that's enough functions of today for today. Can you guys still function?